Hello ladies and gentlemen, what I'm going to show you how to do today is how to determine if a molecule is polar or non-polar. So in order to determine that, what you have to do first is you need the Lewis structure for the molecule. So what I've done is I've got 3 example problems that I'm going to work through today, and I'm going to show you how to use kind of a flow chart or like a concept map to help you decide whether a molecule is polar or non-polar. So we're going to start with this first one up here. So the first thing you need, again, I guess by the end of this video, what you should be able to do is you should be able to determine, based on looking at the Lewis structure of a molecule, you should be able to determine if it is polar or non-polar. So I'm going to start with this molecule first. So my first molecule is NCl3, which would be called nitrogen trichloride, excuse me. And so what you're going to do is the first thing you need to do is consider the bonds and if the bonds themselves are polar. So remember, in order to do that, what you have to do is you have to write or get the electronegativities for each element. So you can do that by using your periodic table. So I want to cut away from that video just shortly. You're going to use your periodic table to look at your electronegativities. Now there's multiple ways you could look at it. You can use the periodic table that I gave you, or you could use just like a search on the internet. Either way is fine. You should get fairly accurate electronegativities, whichever source you use, but if you need help finding that, just make sure you let me know. So I'm going to look up the electronegativities for my nitrogen and my chlorine. So for nitrogen, I look on there, and inside its box is 3.04, which means nitrogen's electronegativity is 3.04. And then for every chlorine, it is 3.16. And I'm going to subtract those. So I'm going to do 3.16 minus 3.04, and I get 0.12. So the difference in electronegativities is 0.12. Now, in a previous video, we went over kind of the ranges of non-polar, polar, and the ionic spectrum. And remember, if the difference between 2 atoms' electronegativities is less than 0.5, we consider it to be a non-polar bond. Then if it's in between 0.5 and 1.7, we consider it to be polar. And then if it's anything greater than 1.7, we consider that to be ionic. So when we're asking, is this a polar molecule or not, really we're asking ourselves, is it in the range between 0.5 and 1.7 difference in electronegativity? So for this one, it's 0.12, which means these bonds in here in a nonpolar, or in this molecule, would be nonpolar. So I'm going to show you how to use this flow chart to help you determine if the molecule is nonpolar. So we can determine if the bonds are polar or nonpolar, but then how does that determine if the molecule is polar or nonpolar? So I'd like you to look over here for a second. So you're going to ask yourself, does it have polar bonds? So for this molecule, we just looked at them, we compared the electronegativities, and we got that our polarity difference was 0.12. So then you can answer that question, does it have polar bonds? And the answer would be no. None of these bonds are polar. If that is the case, if your answer is no, then that means this molecule is automatically a nonpolar molecule. This molecule is nonpolar, we can stop right there. Now if you ever want, like if I asked you for an explanation, why is it nonpolar? You'd say it's nonpolar because all of the bonds are nonpolar. And that would be enough to say this is why it's nonpolar. So let's look at this next one, HF. So the first thing I need to do, look up the electronegativities of each of my atoms, and then determine if my bonds are polar or not. Because it's asking, does it have polar bonds? That's the first thing I consider, does it have polar bonds? So hydrogen's electronegativity is 2.2. Fluorine's electronegativity is 3.98. So I'm going to subtract those electronegativities. And I get 1.78. Now, you might say, whoa, wait a minute. We're looking for elements that are in between 0.5 and 1.7. This is actually greater than that. This bond, technically, based on that spectrum, would be considered ionic. But when talking about if it's polar or not, even if it extends out of that 1.7 range a little bit, we would still consider this bond to be polar. Ionic is kind of like an extreme polarity. Okay, remember we talked about it being like a spectrum. Okay, so we would still consider this bond to be really very, very polar, almost even to the into the ionic range. So this does have polar bonds. So we'd say yes, it does have polar bonds. So then, does symmetry cancel out this polarity? Well, in order to talk about symmetry, what we have to think about is molecular geometry. So what I have to think about is, what does this molecule look like? Well, if I were to get a little model of this molecule, it looks something like this. Okay, so I'm going to use it as my hydrogen will be my yellow one, and this black one will represent my fluorine. Okay, so what's happening here is electrons are being pulled towards this fluorine. So I have like a partial negative charge here and a partial positive charge here. So what that means is electrons are being pulled that way. Well, so does it have polar bonds? I would say yes, it does. Does symmetry cancel out the polarity? Well, when I ask that question, what I mean is, since electrons are being pulled this way towards the fluorine, is there something that's canceling that out? Is there something that's pulling electrons back that way? And the answer would be no. There is no polarity that's canceling out, or there's no symmetry, excuse me, that's canceling out that polarity. There's nothing pulling electrons back towards the hydrogen, or there's nothing counteracting that pull of electrons, which means since there's no symmetry canceling polarity, so the answer would be no, that means this molecule will be polar. Okay? Then, my next one. My next one says that I've got carbon dioxide, CO2. So I've got my Lewis structure. Then I'm going to ask myself, does it have polar bonds? Well, what I need to do in order to determine that is I need to look up the electronegativities. Well, carbon's electronegativity is 2.55. And oxygen's electronegativity is 3.44. And then I'm going to subtract those because they're the same atom. I'm going to do 3.44 minus 2.55, and I'm going to get 0.89. So my electronegativity difference between both of these bonds is 0.89. Does that fall into the polar range? Yes, it does. So here's what that means. That means electrons are being pulled away from the carbon towards each oxygen. So I'm going to have electrons being pulled this way and electrons being pulled this way. So that means I'm going to have a partial negative charge here on each oxygen, and I'm going to have a partial positive charge here on my carbon. Well, so does it have polar bonds? We answered that question. Yes, it does, because 0.89 is in between 0.5 and 1.7. So yes, it does have polar bonds. Does symmetry cancel out the polarity? Well, let's look at the molecule. Here's the molecular geometry for carbon dioxide. I've got my carbon in the middle and my oxygen's on the outside. So notice how electrons are being pulled this way and that way. So it'd almost be like a tug of war, right? You'd be pulling on the electrons, but they're pulling in opposite directions, and the strength is equal. Okay, because both the difference in electronegativity for both of these is 0.89. So if electrons are being pulled this way with the same strength as they're being pulled that way, well, what does that tell you? Well, that tells me that symmetry does cancel out my polarity, because I've got one oxygen on this side and it's pulling on the electrons. I've got another oxygen on this side and it's pulling the electrons, and they're both pulling at the same strength. So what that does is that doesn't create any pulls on the electrons. Okay? So that means that we've got really kind of a balance out of the pull of electrons. So this molecule, even though it has polar bonds, this molecule is actually going to be nonpolar. Okay? Hopefully that was helpful. Again, if you have any questions, please let me know. I'd be happy to help as you complete some of your problems. Thanks for watching.